That's how chemistry is. Yes? Every unit has all the things. You guys need to tell me if it's like all askew like that. There we go. Okay, if you have not yet gotten your new book, go get a new book and a new answer key. Did you guys get your new book? No. Give it to her. She's going and getting it right there, right there. Put her on her desk. There we go. Perfect. Okay. So, electrolytes. Where do we find electrolytes? We find them in Gatorade. Of course, we all know that. We find them in your body. We find them in seawater, in batteries, and plants. All they are is things that conduct electricity where? In solution, right? There are other things that conduct electricity. Metals conduct electricity. That's why your wires are made out of copper. They're not made out of an acid. Right? It would be they could be made of gold, but that's very expensive. Gold is an excellent conductor, actually, but yeah, super expensive and relatively soft metal too. So not so good there. So any current electricity is the movement of charged particles. If we have a wire, so if this is a copper wire, the charged particles that can move are the electrons. Yes? But solutions are not metals. They do not have freely moving electrons. So the freely moving charged particles are the ions. Okay, and so what types of solutions have freely moving ions? You know at least two of them already. Freely moving ions in solution. It's on your test tomorrow. Acids. What else? Bases. Anything else? Salts. And what is a salt? Not NaOH. NaOH is a base. Well, NaH. But not NaOH. NaOH is not a salt. NaOH is a base. Salts are ionic compounds. That don't have hydroxide in them. Okay? Okay. And what does this look like in solution? What it looks like, here we have a battery. And you can see we have the positive terminal of the battery on the right. We have the negative terminal on the left. So the electrons are attracted to which terminal of the battery? The positive terminal, right? Because they're negative. Okay, and what can we say about the electrons and the negative terminal of the battery? The electrons are They're not attracted to the negative terminal. They are, what's the opposite of being attracted? Repelled by the positive terminal of the, where the what? Oh, right there. Fantastic. Thank you so much. Okay, so you get ions in solution by dissolving either ionic compounds, acids, or, forgot to put this one in, bases. And you can see in solution, here we have our ions. We have a cation. And the cations move towards the negative terminal of the battery. And the anions move towards the what do they move towards? Positive terminal of the battery. Yes. Is any of this seeming new and different, or is this just review? This is review? Okay. All right. Electrolytes can be dissolved salts. Salts are ionic compounds. They are made of, you should know this by now, a metal. They either start with a metal or they start with ammonium, NH4+. And then there's some anion at the end. Acids, now acids are molecular compounds. That's kind of weird, right? Because they do produce ions, but they are considered molecular compounds. But they dissociate into ions in solution. Yep, that's weird. How do you recognize an acid? It starts with H or ends in COOH. So in order to have an electrolyte, also bases are electrolytes. NaOH gives you Na plus OH minus. We could have a weak base too. NH3. That doesn't look like an electrolyte, does it? But NH3 is a weak base. So what does it react with? In water. Acids, yes. But what does it react with when we put it into water? It reacts with water, yes. What does it become? NH4 plus OH minus. What did we get? We got ions, yes? And therefore, weak bases are also electrolytes. Even when the weak base itself doesn't have a charge, it will ionize and produce ions, okay? So you can recognize the formula of an electrolyte. It's going to start with a metal or NH4 or H, or it is going to end in COOH, or it's going to be a weak base. But for this unit, doesn't really matter, okay? Not important in this unit. We'll bring back the weak bases in unit 5, okay? But for this unit, you can kind of be like, weak bases, bye-bye. What kind of this is an ionic compound. What state is it? Take a look at the picture. What state is it? That is a solid. This is NaCl solid. Is it an electrolyte? Electrolyte? Electrolyte yes, electrolyte no. Chat with your neighbor. You can go back to the previous page and look up the definition of electrolyte again if you want to. You should memorize the definition of electrolyte. Okay? I'm definitely going to ask it at least on a quiz, if not on a test. Yeah, but is this an electrolyte? No. Solid ionic compounds do not have mobile ions. That says mobile. It looks like a nobile. I'm going to make that M look like an M. Okay, so solids cannot conduct electricity because they do not dissociate or separate just as they are. Aqueous ionic compounds, though, if we take that solid, NaCl solid, and we throw it in some water, so we now have NaCl aqueous, are these ions capable of moving now? Yes. Okay, and you should be able to write the dissociation equation for any salt. Okay, this is again review. So if you have NaCl, how do you write the dissociation? Na plus aqueous plus Cl minus aqueous. This unit, all your states really matter. Okay, in this unit, your states matter. So put them everywhere. Yes. Freely moving. Yep, mobile means freely moving. Good question. Now, if there's no electric field, they just move around randomly. But if we apply an electric field like we did back here, then you'll get directionality. You'll get the positive ions moving one way and the negative ions moving the other way. All right. Acids do the same kind of a thing. What state would this HCl be? What is it?
Pure acid form.
That's a gas. It's a small covalent compound. Small covalent compounds tend to be gases at room temperature. Not all of them. Water is not a gas at room temperature, but it's got really strong intermolecular forces. It's got hydrogen bonds. Okay, so if you're taking biology, that probably means something to you. And if it doesn't, then you don't need to worry about it. Okay. Small covalent compounds tend to be gases at room temperature. Again, you don't need to know that, but you know, kind of good info. Now, if we take that gas and we dissolve it in water, we end up with HCl, aqueous, and we have the ions, and they are all freely moving, therefore they are mobile ions. And we should all be able to write the dissociation for that. HCl goes to H plus Cl minus, aqueous. In this case, it happens to be a gas, but very often it'll be an aqueous. If you've got what do you call it? If you've got a weak acid, the weak acid is dissolved, so it is also aqueous. Okay. I wouldn't worry too much about the fact that HCl is a gas. Don't get wound up about how do I know that HCl is a gas? You're not going to be asked something that you don't know. Okay, I might say some gaseous HCl is added to water, and then you would know. Yes? Okay. Covalent compounds and covalently bonded elements are they electrolytes? Covalent compounds? No. Why? What do you need to be an electrolyte? You need freely moving what? Ions. Electrolytes need freely moving ions. Do covalent compounds have ions? No. So how could they be freely moving if they don't exist? Yes? Can't have freely moving ions if there's no ions to move. Okay, so let's say this is solid I2. So this is an element, but you could do the same thing with solid carbon dioxide or something like that, although carbon dioxide is complicated because it reacts with the water. So we're not going to talk about carbon dioxide. We'll just talk about I2. If you take it, you've got your I bonded to your other I. What kind of a bond is that? That is a covalent bond. What happens in a covalent bond? What's happening with the electrons? The electrons are shared. If we were to draw a Lewis structure of this iodine, how many valence electrons does iodine have? Look on your periodic table. Iodine is in group 17. Therefore, how many valence electrons? 7
Oh, it needs one extra, yeah.
valence electrons. So iodine is going to look like this, an iodine atom. This is the Lewis structure. 1, 2, 3, 4, 5, 6, 7. Does that look familiar? Yes? Is that a stable, happy structure?
No.
No. And if we have another one, is that a stable, happy structure?
Oh wait, like the bonds. Yeah.
What can these guys do?
They can
They can
bond.
bond. We can get those two electrons to share. And if we're drawing the Lewis structure, we can replace those two dots in the middle with a line. Okay, so that's an I2 molecule. And here we have our covalent bond. Is there any way that this thing is splitting up into ions? No, cannot split into ions. So that's why this thing is not going to be an electrolyte, because there's no ions. Now, if we have iodine solid, you'll notice we've got little pairs of iodines. Those are iodine molecules. We have an iodine molecule here, I2 molecule. What is holding the I2 molecules together to one another? What holds one I2 molecule to another I2 molecule? Some sort of force. Intermolecular forces, yes. Inter is between, intra is within. Are intermolecular forces strong or weak? Intermolecular forces. They are weak. Relatively weak. So water can come in and offer I to some other intermolecular forces. Okay, intermolecular forces are kind of like magnets. Where's my magnets?
Ever have to write like imperial formula?
Huh?
Like I remember in grade 11 we had to like write imperial formula.
Empirical.
Empirical and the other one.
Yeah, we don't need to do that this year. Okay. So what'll happen is that when you take the I2 and you put it into the water, so in between here, those are IMFs, intermolecular forces. Okay, that hold those together. Now we take the iodine and we dissolve it in water, and there's going to be like a little water molecule here. What is wrong with this thing? Why does it keep erasing on me? There's a little water molecule, and guess what we have in between the iodine and the water molecule? We also have IMFs, new IMFs. Are you going to need to be able to explain any of this intermolecular force stuff for Chem 12? No. Okay? What you need to know is that if you have a covalently bonded substance, it does not split into ions. The molecules separate from one another. Yes? And that process of the molecules separating from one another is called dispersal. They disperse. Have you guys heard the expression, the crowd dispersed? What is the crowd doing if it disperses? Everybody's just, right? So all those little molecules are just, they're going off each in their own direction, okay? And in order to write a dispersion equation, we start with I2 solid. What do we end up with? What kind of particle do we have? What is that? That's still I2. I2. And what's different? Aqueous. So when you have a covalent compound, there's no change to the formula, there's only a change to the state. So there's no freely floating charged particles. And so therefore, because the iodine molecules are neutral, so it will not conduct electricity. Therefore, I2 is a non-conductor, is a non-electrolyte. Is good? Any questions? Okay, therefore, all covalent molecular solutes, are non-electrolytes except acids and weak bases. Well, and bases. Let's just put and bases. Pure water, electrolyte or non-electrolyte? Even though water does dissociate a little tiny bit, how much ions do we actually have in solution? Like with pure water. We have 2 times 10 to the negative 7 molar ions, yes? Because we've got 1 times 10 to the negative 7 molar H and 1 times 10 to the negative 7 molar OH. So water is a non-electrolyte, even though a tiny amount dissociates into H plus 1 times 10 to the negative 7 molar and OH minus 1 times 10 to the negative 7 molar. It's not enough to conduct electricity. Did I haul out the conductivity apparatus earlier this year? The thing with the light bulbs? I'll show you what it looks like. This thing? Have we looked at this? No. Okay. I don't want to do it today. Can we do it on Monday? It'll give us something to look forward to on Monday. I just don't want to I don't know. I should clean up this space before I do it. Yeah? Yeah. Okay. We'll do this on Monday. We'll look at some actual things and see how they conduct electricity or not. Well, what? Why am I not doing it today? Because my desk is like that. You'll help me clean it? Okay. Okay. We really just need to move everything. It doesn't need to be organized. Isn't it the same thing?
Yeah.
Just put everything in a pile.
Okay.
Okay, and then you can just move it over there.
Yeah. We'll keep it organized. Don't worry. It will not mix. Right here.
They can go here.
At the top. I'll get another pen.
I'll take those. Thank you.
Calculator.
Yeah, that can go over there. Let's go there.
Yeah, boom.
See?
Now
Okay, good. That was painful for me to do on my own, though. That would have taken like 4 times as long. All right, so let's look at this today. Okay. So this is a conductivity apparatus. It has 2 wires. Those are like the electrodes, okay? And we're going to plug it in. Right now I'm going to turn it off though, because I don't want to electrocute myself. Yes, if it were plugged in and turned on and I did that, I contain enough ions that I would conduct electricity quite nicely. Yes, and I do not want to do that. So right now it is turned off, but I am going to plug it in. And we're going to get some, okay, substances to work with here. And actually, this is relevant to your test tomorrow because it has to do with concentration and strength of acids, right? So if I have, let's see, what have I got here? I've got 1 molar, 1.1 molar ethanol, 0.1 molar, 0.1 molar, 1 molar. Okay. All right. Okay. You guys are going to do some predicting on how bright the light bulb is going to be. Okay. Ah. Okay. We have 1 molar HCl. You guys are going to predict whether you think that this is going to be, let's see, I'm going to unplug it just for a moment. Because even though it's off, I don't trust it. Because I actually did zap myself once on a different version of this that we had at Alpha. It made me very unhappy. Huh? I taught at Alpha for my first 5 years. Yeah. And then I moved here, and I've never moved since because I live 10 minutes from here. And I live like Coquitlam way, so I don't want to move to any other Burnaby schools because they're further away. All right, you guys are going to predict whether this is going to conduct electricity or not. Actually, let's start with water. H2O. What's going to happen with our light bulb? Nothing. Okay, so it is plugged in. No, it's not. Something's wrong with these plugs. Okay, now I'm going to turn it on. There we go. Here comes the water. Ooh, look, nothing. Yes, confirmed. All right, shall we try the HCl? 1 molar. Predict what you think is going to happen. Is it going to light up, not light up, or light up dimly? Okay. So you guys get to say if it's going to be bright, dim, or not lit up. Bright? Okay, let's see.
Oh my god.
Right? Bright. Okay, and I'm going to use the water for rinsing off in between. Okay, so 1 molar HCl is bright. Now I have Now I have 1 molar CH3COOH. What is that? What's the name of that compound?
I don't know, Bonfield.
That compound is named? You should know it. Sorry? Ethanoic acid, also known as?
Acidic.
Acetic acid. Acetic. acetic. Okay? Acetic acid. Is it going to be bright, dim, or not? Okay, let's find out. So indeed it is dim. And it got bright at the end because the two wires touched. Okay, that was what happened there. So even though this was 1 molar, it was dim. Why was it dim in comparison with the HCl?
Because it looks like a weak acid.
Because it's a weak acid and mostly unionized.
It's like dissociates partially.
Yep. Only partially dissociated. Okay. Now we're going to take HCl, but we're going to go 0.1 molar.
Is the molar?
0.1 molar HCl. You're going to think to yourself, is it bright? Is it dim? Not lighting up?
Probably still bright.
What do you guys think?
Still bright.
Well, let's try it and see. Make a prediction in your mind, even if you're not willing to commit to it out loud. Like make a commitment in your brain just to be like, this is what I think. Okay?
Yay.
It is
Right.
bright. Why is that?
Because it's still strong.
It's still strong acid, even though it is 10 times diluted. Yes? Now, I'm actually going to try diluting it a little bit more. Okay, so I'm going to do another 10 times dilution. It's going to be very ballpark, this dilution, okay? I've put in approximately 8 milliliters, and I'm going to fill it up to 80, okay?
Oh, this one you can draw your hand in.
Hmm?
Oh, like the example you gave us. It's like, oh, I touched hands with hydrochloric acid.
So this is another 10 times dilution. So this is 0.01 molar HCl. Let's see what that's like. Okay, we finally gotten to a point where it is more dim. Okay, but we had to dilute it 100 times. Yeah, before we got there. But we can get it so it is similar to a weak acid of 100 times more concentrated. Okay? All right.
But it's still considered a strong acid.
It's still a strong acid. It's still considered a strong electrolyte because it tells you how much it's going to conduct, and that will change based on its concentration. But yeah, it just tells you how much it dissociates. Okay? Now we have some other things here. I have some 0.1 molar acetic acid, 0.1 molar. Okay, 0.1 molar acetic acid. What do you think this is going to be like? Let's find out.
Oh, like a very slightly there.
Okay, very dim. Yes? Now let's play with a few things. Because these are kind of like our acids. Oh, let's do a base. 1 molar NaOH. What do you guys think? 1 molar NaOH.
Yes. Right.
Right, Jim?
But that's not good.
Stop another time. Where did it go? There it is. Okay. Yes, because metal hydroxides are strong bases. What type of base? There's 2 types of bases. What are the 2 types of bases? Arrhenius and Bronsted-Lowry. What kind is this? Arrhenius.
Most Bronsted-Lowry bases are weak, I believe.
All Bronsted-Lowry bases are weak except for NH2 and O2 minus. O2 minus up at the top, not O2 minus, but O2 minus. Okay. Let's try ethanol. Which is CH3, CH2OH. And if you are on your phone instead of paying attention to this, get out of my classroom. Like, why would you be here if you don't want to be involved? Ethanol. What do we think? This is an interesting one. Got no OH at the end. What kind of bond is there going to be? What kind of bond is that between the carbon and the oxygen? An ionic bond, because we get ionic bonds between nonmetals and nonmetals. What kind of bond is that between the carbon and the oxygen? That is a covalent bond. Non-metal, non-metal, covalent bond. And when we have covalent bonds, what's going to happen? Do they split up? No. So is it going to conduct electricity? No. Let's see if our prediction is correct. Nada. Okay. When you have hydroxide attached to some carbons, that's not a base, that's not a hydroxide ion. That's what we call a hydroxyl group. And this is a type of compound known as, anyone know what it's called? With an OH, an organic compound with an OH in it is called an, there's a clue in this name, ethanol. It's an alcohol. It's an alcohol. So you should be able for this unit to recognize the difference between an alcohol's formula and a base's formula. Base, what does a base need at the beginning? Metal, or NH4. Yes, because that's also a cation, right? You need a cation and hydroxide for it to conduct electricity to be a base. But if you have nonmetals with OH attached and the nonmetals are not NH4, then it is an alcohol, okay? And it will not conduct electricity. Let's try CuSO4. What's our concentration here? 0.1 molar. What do you guys think? Oh, that's not my water. That's my diluted HCl. Let's rinse it again with the water this time. And that's why we label our beakers, because they both look like water. Okay, so anytime you do a lab, you should label your beakers. We will do a lab at some point eventually, I promise. What do we think? Bright? Dim? Nothing?
Nothing wrong with it. Oh wait, probably bright.
Chat with your neighbor about it. Have a discussion.
Yeah, you can divide it. Yeah, you can divide it.
Are we ready? It's bright. Why is it bright? It's an ionic compound, so it dissociates into ions. This is CuSO4 is what type of compound it is? An ionic compound, which we can also call a salt. Okay? All right, let us try. Ooh, this one's fun. KSCN.
What?
1 molar.
Why does that sound like? Why does that look like?
Chat about that one.
Probably dim.
Anyone? Okay, let's find out, shall we? What kind of a thing is K? It's a metal. So what kind of a compound do we have here? Ion. Oh, yes, ionic. Yes? KSCN is a salt.
No, that's yeah.
Thiocyanate. So if you look under SCN, if you look under T for thiocyanate, you will find it in your table of ions. SCN minus K plus, SCN minus. But you don't even need to know because you know it starts with a metal. Therefore, it must be an ionic compound. And that means that SCN must be your negative ion. Okay? I don't think we need to do that. Do we? Yeah, okay, let's watch the videos. Oh, okay. Ugh. Okay, this is what? 3.1a. What? Oh my God. Sorry. This is messing with me. Okay, 3.1a. Sorry, I need to get the link here. Oh, this one is just this guy doing the same thing that I just did. So we don't really need to do that. Let's try the dissolving of solid sugar. And do we have any sound?
I was just talking about that. Last year, Mr. Nani showed us a video of like putting pure sodium into a toilet or something, and it.
Okay, so here's our sugar. When the sugar is added to the water molecules surround the sugar. Due to the strong attraction between the polar water molecules and the polar sugar molecules, the water molecules are able to pull the outer sugars away. So let's go back here. As the outer layer of sugar molecules are pulled away and surrounded by water molecules, the next layer of sugar molecules in the crystal are exposed to the water. So you're getting intermolecular forces. So if you had a solution of sugar water, and I never use the sugar water because it goes moldy. So like you can see it's like gross at the bottom. So I never do the demonstration. You got to make it up fresh every time. So I never do it. But would sugar water conduct electricity? Sugar is C12H22O11. No, because it is a covalent compound. What is breaking when it dissolves? Intermolecular forces, yeah. So the molecules stay intact. And you can see the molecules are just dispersing, just like a crowd disperses. Okay, enough of that. Dissolving salt. Okay, let's try this one. Why do I not have
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Is good?
When an ionic substance...
No, don't do it again. Okay. Okay. And let's take a look at the movement of sodium and chloride ions in solution. I don't know if this one's worth it. Let's try it. This one's kind of goofy, I think.
Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water, positive hydrogen ions and negative hydroxide ions. These different charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive. Sodium and hydrogen compete to gain electrons. The hydrogen ions win out. They lose their positive charge and form bubbles of hydrogen gas. Competition also happens at the positive electrode. This time, chloride ions win out, losing their negative charge and forming bubbles of chlorine gas. Industrially, the electrolysis of sodium chloride solution.
Okay, so we don't need that anymore. You just got a little preview of Unit 6, electrochemistry, where you have the transfer of electrons through a cell like that, okay? But you don't need to know that yet, so let's not worry about
Can
it.
provide.
Okay. And then there's some exercises here. And I think that's it for today. So today is Thursday. Over the weekend, You can do the exercises in 3.1a. Yes, because tonight you're going to be studying for your test. So 3.1a is your homework over the weekend. Oh, you know what? You could also do You could also do 3.1b. 3.1a and 3.1b for the weekend.
Do you have extra copies of the
Of the first quiz?
Yeah.
Probably.